Crystals like snowflake and diamond are ubiquitous in nature. The atoms or molecules in a crystal are periodically arranged in real space. For example, we cut the crystal shown on the left and label the atoms on the cut according to their position coordinates x, y shown on the right. In this way, we can generate a lattice structure in 2D real space. Crystals can also exist in other dimensions like phase space or time. Let's first consider a single atom trapped in a harmonic potential. In the ideal condition of no driving and no dissipation, the atom oscillates with the fixed quadrature xp given by the initial condition. Then we can label the atom in the phase space as shown in the right. We can put more and more atoms free of interaction randomly in the trap. The configuration in the phase space shows no particular periodic structure. However, things will change if we add external driving field. If the driving field is a multiple of the harmonic frequency, the atoms could be arranged periodically on a ring in the phase space, as shown in the right. The reason is that the effective potential generated by driving field shows a Z-in lattice. If we change the types of the driving, other more complicated structures can be generated in phase space. For example, the multiple Z-in lattice, square lattice, hexagonal lattice, and even quasi-crystal lattice. Each stable point of these lattices represents a possible subharmonic mode with a fraction of the driving frequency. The robust subharmonic mode is called time crystal since it breaks the discrete time translation symmetry of the driving system. The phase space lattices are fundamentally different from the real space lattices, since the two dimensions of phase space x and p are non-commutative in quantum mechanics. In the non-commutative space, the concept of point is meaningless. Instead, we should define a coherent state. If we move the coherent state along a closed path like a triangle, the final state has an additional phase factor with the phase exponent s being the area of enclosed path. This is similar to the AB phase for charged particles in a magnetic field. Therefore, we say the phase space has an intrinsic magnetic field. In order to further investigate the many-body dynamics, it is important to figure out the effective interaction in phase space for a given type of interaction between atoms in real space. We found that the effective interaction between two atoms I and J on the rotating wave approximation is just the average real space interaction during one time period. It is important to notice that the effective phase space interaction is only a function of their phase space distance Rij, which does not violate the phase space lattice symmetry. Based on the phase space lattice, phase space interaction, and non-commutative geometry of the phase space, many condensed matter physics models can be developed in phase space or time crystals. For more details, please read our review paper to be published in New Journal of Physics.